Today, we'll be chatting about the task specification problem, and we'll also be coming back to some topics, that we had covered before, but there were still some missing pieces. Specifically, some things on robustness and generalization. There was, the plan was to have a lecture discussing about what to build in. We'll have some discussion. And if we have time, we'll also get into a bit of curriculum learning and types of uncertainty. So let's get started. Since there might be a question on the chat. How much do I agree with Leslie's take on the future of RL? That's a good question. Let's wait for it for the end of the lecture, and then we can go in a free flow discussion at that point. So consider, you want a bottle of Coke, and obviously there is a robotic system that you want us to fetch this bottle of Coke, right? So if I give an instruction in language, then the robot must first interpret, want a bottle of Coke, right? And this it can do, say, using natural language processing. And it needs to understand, what is Coke? And second, where is the Coke? Now, as we have seen in this class, but also in other classes, that our object detection systems today are pretty good, right? So they can figure out what a chair is, what a table is, and so on with high accuracy. The second question which we need to figure out is, where is the Coke, right? And this is a matter of common sense typically, right? Because we know that Coke might be in the fridge is in the kitchen, so on and so forth. The question is, how would this robotic system have this kind of common sense knowledge? And so what should the robot do? Any suggestions or ideas on, from where we could get this kind of common sense knowledge? No? YouTube videos. So that's a good suggestion. So one thing, in this class that we have discussed is how we could leverage how people do things in YouTube or in, videos and imitate it. Right? Now, that is one possibility. For now, let's also consider another possibility, which is using language models. Now, what are these language models? I mean, many of you might have heard these terms GPT-2, GPT-3. What these models do essentially is that they condense large amounts of text data. Or when I mean condense, what they do is they would, take chunks of text data and try to predict, for example, given 3 words or 4 words, what will be the 5th word which comes up, right? Or they might try to predict the word in the middle. So they pose a self-supervised task or a generative task where they try to predict future words, and that task is used for learning features. And it's similar to how autoencoders are used for learning features in image domain. Language models are used for learning features and information about the text. And some of the more popular models were GPT-2 or GPT-3, if you heard about them. Right, so what can these models do? Right, given the question or the sentence, the Coke is in, we can ask these models to complete the sentence. Right, so for example, if we put this to GPT-2, we get the Coke is in the bottle of a small empty bucket, according to. Doesn't make a lot of sense. And let's change the question and say, buy a Coke at, might say the gas station down the road from mine. Now this seems very sensible. Right? This is something that, we all know about the world, that, Cokes are available at the gas station, and something which the model also predicts. Let's say one more example, the Coke is in, it says the fridge with the rest of the food. Again, sounds very sensible. Let's try, one other word, the toaster is in, says the microwave oven, the toaster is in the microwave. Doesn't make a lot of sense. It's maybe like a bunch of words put in this, just thrown together. And then you say to get out, you need to it says go through the door, mark the tunnel. Right? Maybe it watched or it got a lot of text from movies where people were escaping through the tunnels. That's the point of me showing these examples, is that to some extent, we can answer a few questions with help of these language models. And there's some questions, which the output is still garbage. And so sometimes it may work. And this is an active area of research. How do we improve our language models? And if you want to learn more about it, please take the NLP course, and they're going to discuss a lot about it. But let's assume that this works. Let's for a moment assume that the language model is working fine. Right? And let's assume that we got a language model and it gave us a recipe to make a pancake. Right? So it gave us a bunch of instructions on how to make a pancake. Now, let's see an example from this movie called Short Circuit, where this robot is executing a set of instructions which you could reasonably think could come from an instruction manual, or for example with automated methods like GPT-2 or GPT-3. Right? So let's see what happens.
Okay, to make these golden fluffy pancakes, add flour, milk, and eggs.
You're able to hear the audio, right? Hopefully. So that will have most of it.
Mix thoroughly.
Right, so over here, the robot is not realizing that it needs to actually, break these eggs before it puts them. Right? It just puts the egg and tries whipping them.
Still lumpy. Marvelous.
Well, none of us are going to think of this as marvelous, but the robot does think because it followed exactly what the instruction said. To put the eggs and then whip it. It did exactly that.
For crisp yet moist potatoes, brown on one side, then turn over. This.
So now, again, it is following the instructions, but it forgot a lot of things which the instructions implicitly assumed. For example, when you turn over potatoes, you first take them out of the box, and then you don't turn over the pan, but you actually turn over the potatoes. Right? So these things are again things which we as humans know about the world, because we have lived in the world for a long time. But if I just get a recipe for pancake, that information is not going to be there. Right? So what is the point I'm trying to make? The point I'm trying to make is that there's a big assumption that we can get a high level plan first, but even if we can get the high level plan, executing this high level plan is going to be a hard problem, right? Just because of the kind of instances we saw, right? We had a high level plan of how to make a pancake or how to make potatoes, but executing those skills in the plan is non-trivial. And most of this course so far has been on how to learn these low-level skills. Right? And what we're going to now see is some of the challenges which are involved in getting the agent to learn the low-level skills in the manner we want it to learn. Right? For example, we wanted this agent to whip the eggs, but it did not break the eggs before putting them, right? But so it's doing a low-level skill, but not in the way we want it. Any questions? Any comments? Before we proceed.
So would you say it's more of a reward shaping issue, that like you want to design the optimal reward functions or the intermediate goals so that you can cue it in the right skill learning direction?
So it is a reward design issue. And what I'll try to communicate is that telling a machine what to do is actually quite hard. And that is true across, reinforcement learning, supervised learning, and so on and so forth. Right? So there's some notion that we want to communicate or what we want the machine to do. So what are the challenges in communicating that to the machine? Right. So the one thing, maybe Ayush, give me maybe like half an hour. If this question is still unanswered, we can come back and discuss it. But that's kind of some examples I'll go through. Right? I mean, we have seen this example before. And if I wanted this agent to walk and walk right, I can give it a reward to move right. But we saw previously that it can learn this unintended behavior of falling on the ground and then moving, right? And we saw this as an issue in the reward shaping assignment and saw how carefully we have to shape the rewards, right? And this is what we call as, grad student reward descent, where someone just needs to observe the behavior, change the reward, and do this loop for a very long time to get an agent to behave in a particular way. Right? So in some ways, if I were to be pessimistic, I can say a lot of reinforcement learning is about fitting reward functions to algorithms instead of actually designing new algorithms. And a lot of, in practice, this is what people end up doing, right? Now we saw some approaches which try to learn the reward function, like by observing some demonstrations. So we studied imitation learning, we studied inverse reinforcement learning. That was partially to mitigate this issue. Now, in the same vein, there is one more line of work which is worth knowing, which is using human feedback to classify which behavior is the one that we want and which behavior is the one that we don't want. Right? So instead of learning the reward completely autonomously, now we're going to involve a human. Now, how we're going to involve it is we're going to show the human two behaviors, say one on the left and one on the right, and just ask the human which one of them is better. Is the left one better or is the right one better? And that is the supervision we are going to use to learn a particular skill, right? So for example, over here, we are trying to make this hopper, do backflips. So one possibility is to design, a reward function, which we know is a tedious process. We can do reward shaping and, maybe get this agent to do backflips. The other process, what we can do is preference-based learning. So what is this preference-based learning? As this agent is training, I'm going to show the human, two trajectories and ask him to choose which one of them is better. And I'm going to use the ranking of the trajectories to learn a reward function. Now, again, I'm not going to go into details of this work, but I think I would refer you to the paper, Deep Reinforcement Learning, from Human Preferences, to read about this body of work. Now, this even if instead of designing a reward function or instead of doing IRL, or I can ask the human to give preferences on which one is better, but that's also problematic. Right? Why is it problematic? Because from the human feedback, what is the human feedback telling me is in these two videos, video one is better than video two, right? So from that feedback, I still need to figure out what is the most important thing in the video, right? And this can be hard. For example, we saw this particular example where this guy was pouring water, and what we reasoned was that there are many things changing in the environment, right? There's a table which is moving, there's water which is pouring out, the hand of the guy is moving, right? And then the bottle is near the beaker. But what is important is the water goes inside the beaker, and it's unclear, that is the information I need to care about, right? Because if I just look at the pixels in this video, the number of pixels in the table are much larger than the number of pixels of the water flowing from one bottle to the other. So now what is the point? The point is, if I want the agent or communicate to an agent a particular task, I can design a reward function, but that will be tedious. If I'm willing to do reward shaping, then all in good. Or we can go down to inverse reinforcement learning, imitation learning, or learning by preferences. And these are going to have this ambiguity problem to identify what is important in this video to focus on. So again, it's a problem in specifying what is it, the task that I am demonstrating, and how does the robot understand that. Similar thing, we also observe in model learning. So if we, consider, or if we just recap, right, we saw this work in which the robot was pushing these objects, and then we had learned a forward model which predicted, given the image and the action, what happens next. And then when we saw the predictions, what we saw was that most of the effort is on the hand and not necessarily on modeling the movement of objects. So these methods are focusing more on the hands and not on the object. It's again, what we wanted the system to do was to focus on the object motion. What it ended up focusing on was the hand motion. It's again, there is this mismatch between what we wanted the system to do and what the system actually ended up doing. So there's a couple of questions which have come up. So one question is, what about the cases where humans themselves are not able to judge which one is better? Like some task may not have an intuitive answer. So in cases where humans cannot judge which one is better, then we need to rely on some other criteria, right, which could be a reward function in that scenario. Right. So so in that case, you'll end up doing reward shaping, and probably cannot use techniques which rely on human preferences. I hope that answers your question, Siddharth. If I have not answered, feel free to speak up or type in the chat. The other question is, can we replace human feedback with meta learning, or could we use attention with the misfocus problem in this slide? So we could, try to have attention mechanisms, but we'll still have to bias the attention mechanisms to focus on some part of the image, right? For example, it is possible the attention might focus on the hand and not on the object. And there's something which we'll need to build in, which will prioritize the agent to focus on the objects instead of focusing on the hand, right? Just plain vanilla attention may not do the trick. The second comment is, can we replace human feedback with meta learning? Maybe what you're trying to say is, if I have done some tasks before, that might give me a prior that in this particular task, the hand is not important, but the objects are more important. So this is the kind of continual learning / transfer learning that we hope we can do, but unfortunately, that still remains a challenging research problem. But I think that's a good way to think about it, that if I have ambiguity, maybe the way I resolve it is by relying on knowing what is important and what is not important from my previous tasks. So if you, just to put things in perspective, right, if you look at a lot of this machine learning work or learning from control work, it's happening from scratch. So you take one task, you start from scratch and you learn it, right? I mean, that was the first wave which happened. And in that first wave, specifying the task was hard. And therefore we had, a bunch of tricks. Now, what people hope is transfer learning or continual learning is going to work better than it worked in the past. And maybe we can learn some of these things through that. But that remains an open question. or an open challenge. Similarly, let's consider autoencoders, right? What we saw in autoencoders is that they learn features by trying to compress a high dimensional observation into some low dimensional bits. And if I'm dealing with images, maybe, what I'm hoping is I'm going to learn some good features or learn some independent factors which explain how the image was formed. And those factors are going to be good features for doing control or for doing image tasks like classification and so on. Right? So for example, what you would hope is, maybe the shape of this digit is going to be different from its color, is going to be different from its lighting. So these are the things that I would get when I'm trying to learn this code. Right? But what could happen, but the problem is that there are two codes which are equal, right? So one feature representation is to disentangle this image into features like shape, color, and lighting. The other possible representation is just JPEG compression. Right? What is JPEG compression? Just represent the image as some low frequency and some high frequency features which do not have any semantic meaning. Right? So again, we pose this feature learning problem by saying I can learn good features if I can learn a low dimensional representation of my data. But turns out that there are many low dimensional representations of the data, and it's hard to control whether I learn the one that I really want or whether I end up learning something which I don't want. Right? And the network will just choose one of them. Right? The problem is that we don't know which one it will choose a priori. Right? And one of them is a good one, and the one of them is something that may not be very relevant for what we are doing. The same thing also happens with standard supervised learning. Right? For example, consider I want to learn a concept of chair. Right? So we went on the internet, we collected a data set, we said, these are my chairs, we labeled some images as chairs. Right? So now if I go and test this chair classifier on very similar images of chairs which I get from the internet, everything works perfectly well. But then what if I do is, if I now go and get chairs, how chairs would occur in the real world, maybe in some different positions, like the chair has fallen down, or maybe in poses which would be uncommon on the internet. And because in the internet there is a bias that you only put photographic things on the internet. So if I go and collect data in the real world, something which is slightly unusual, then what we find is the performance drops to around 40 to 45%. Right? So what this plot is showing is different models from AlexNet to ResNet, and the dotted lines are showing the performance on ImageNet. I'm sorry, the blue and the green lines are performance on ImageNet, and the red line is performance on ObjectNet. So ObjectNet is this new data set which has chairs in many real world configurations instead of just internet configurations. And what you find is a big drop in performance, which is around 40 to 45%. What this means is that by collecting a big data set of images, what we thought we were learning is a concept of a chair, but what we actually learned was how does a chair look on the internet. And we didn't really learn what a chair is. So if you see all of these examples, what's happening is, as a human, I specify a task objective, I optimize over it, the machine does it, and then we look at the result, and then it's like, what happened? Right? We were expecting a certain behavior or a certain representation to emerge, but we end up getting something different. Right? And the question is, why does it happen? Or in other words, why is it so hard to tell machines what to do? So the takeaway is that this is not a problem which is specific to reinforcement learning or learning to do control. This problem is there in all of machine learning, whether you consider supervised learning, whether you consider representation learning, or you consider sensory motor learning. And we're going to spend, a part of this lecture trying to, understand this question in more detail. Now, before I jump ahead, I'll just take a small pause and see if there are any questions or comments. No, nothing controversial. Okay. So, let's march ahead. So one reason, or one example that we had seen in the previous lecture also is that suppose, we are trying to train a dog detector or a dog classifier. The hypothesis that we want is, given this image, we should be able to detect that, okay, this is a dog because it has a tail and it has eyes. But if I get many images of dogs on the grass, I could learn a spurious correlation that the tennis ball and the grass are what makes this image a dog. Right? If most of my images of dogs were on the grass or playing with the ball, that is, the data set was biased, I could end up picking up on these features. And now, there's a shift in my distribution that I no longer see the dog on the grass, but I see it in the pool. I might confuse it because now I might, use water as a feature, and based on that, I might say it's a dolphin. Right? So this is, again, an illustration of a problem that we have been seeing, that these deep networks are learning unwanted solutions. So the first thing you can say is this because of a biased data set? Turns out that even if you balance the data set, we can still end up learning spurious features. So it's not just about having a balanced data set. So if you want to learn more about it, I recommend reading this paper, which presents a scenario where the data set is gender balanced, but still you end up learning gender biases. Now, to see, to gain some intuition, why that might be happening, I consider the classification task that we want to do over here. So you see some images which are red in color and have a digit 2, some other images which are blue in color and have a digit 6. Now I say this is class A, and I say this is class B. And the goal is to distinguish between class A and class B. So now I have two choices. I can either use color or I can use shape to distinguish between class A and class B. The point to realize is that data provides no information about what feature to use. Should I use color or should I use shape? What should this depend on? I mean, the data by itself is not providing me any information. So one thing you can say is, well, the answer should really depend on the future task, right? Or the answer depends on the task that I've done previously, right? Based on that, I have some prior which tells me which feature to use. But then the question becomes this, okay, if the answer depends on the task distribution, then who is the entity who is defining what a task is, right? Or what is a new future task, right? So for example, we'll consider, one task I have is that I want to push this object to this yellow position. Right? So is pushing to a new location a new task? Or is this a new task? Maybe. So maybe what I care about is changing the location. Or maybe a new task is not about changing the location, but pushing a block of different size. Right? Or maybe that new task is about pushing a block of a different color. Or maybe it is about pushing a block of a different shape. Right? So what a task is and what do we mean by a new task, again, has no global definition, right? I mean, there's no universal definition. It is something which is defined by the human, right? So if I just give you, a data set, I could pick up on any feature, a color or the shape. Now, a human might come in and say, well, the test set I care about is this one, where shape is important, but color is not important. So if my neural network picks up on shape as a feature, everything is going to be good. But if the neural network picks up on color as a feature, then it is not going to generalize. Right? So the question becomes this: what feature does a neural network learn if I give this as the training set? Turns out if you run this experiment, if you train networks on this training set and then you test it on this, the curves you're going to get are shown on the right. So the y-axis is the accuracy, the x-axis is number of training epochs. What you find is the networks learn very well on the training set, and the accuracy is almost at chance on the test set. And so on test set, there is no correlation between the shape and the color. Right? So what this suggests is that neural networks are indeed using colors as a feature to make this classification. So we can go and test this hypothesis where we can make a data set where we just remove the shape and just have color, and the networks predict this perfectly well. And this is not just one network with one random seed. You can try different random seeds, different architectures, change other hyperparameters, but all of these networks find the same solution. That they're not even, it's not the case that some networks are finding shape, some networks are finding color. Almost all networks are finding color as a solution. And this problem has been identified in the literature. And, for example, what people say is different networks learn the same non-robust feature. So what do I mean by non-robust over here? I mean, it's a feature that is not useful in layman terms. Right? And different networks end up learning the same useless feature. Now, this, I think, is a very good paper which summarizes this, and it brings about this issue. Collateral examples are not bugs, they are features. Something we'll look briefly in later part of this lecture. You might say, well, this is something specific to this color example that you created, but how general is this phenomena? It turns out this phenomena is quite general. I can create one more data set where I introduce this, shapes. So all sixes come with triangles, and all twos maybe come with a square. Right? And then we can test on a data set where there's no correlation between the small shape and the big shape. Now again, it turns out the networks pick up on these spurious features instead of focusing on the actual digit shape. So what these examples are showing is that the network will pick up on one particular hypothesis. If there are multiple hypotheses of how to perform a task. Right? Just to illustrate this once more, suppose if I was trying to classify yellow dots from these violet dots, one way to classify is by this hyperplane, which is hypothesis 1. But an equally good way is using this hypothesis 2, which is H2. Turns out there are infinite hypotheses between H1 and H2. That is, the infinite planes, which will all yield perfect training accuracy. So traditionally, how do we choose one of these hypotheses? Right, this is where regularization comes in. Right, we may say we want max margin, which will lead us to SVMs. We might say we want L2 regularization or something else. Right? But what about deep learning? Which one of them will a deep learner choose? Right? Now, this is something unclear because a lot of the regularization in deep learning is implicit. It's not explicit. What do I mean by this? What do I mean is, for example, SGD is a form of an implicit regularization, and it prevents you from getting stuck at a local minimum. And which one of them it is going to choose, it's very hard to reason. Right? This is, for example, in max margin, you can reason that maybe H1 is more likely to be selected because it is max margin. H2 doesn't look like max margin. But with deep learning, the regularization is not explicitly done many times, it's implicit. So it's very hard to go from a deep network architecture and say which of these hypotheses it's going to choose, right? And the correct hypothesis is going to depend on what the test set is, right? So now one thing to think about or to take away is that if I just give you data, there are many ways to get perfect training accuracy. Right? So if you have finite data set and a very powerful machine learning classifier, there are infinite ways in which you can perform that classification. But many of them may not work or may work depending on what your test set is, right? And this mismatch between many different ways of solving a task versus me caring about one of them and me being unable to specify which way of solving the task I care about is what creates a problem. And it creates all the problems that we talked about, like with reward design, to supervised learning, to feature learning. Does this make sense? Any questions or comments? No? So it's an excellent comment that even though there are many hypotheses that can result in the perfect training accuracy, ML can inherently motivate and choose the easiest one. So now the question becomes is what is easy, right? Now defining what is easy is non-trivial because the definition of easy or hard depends on the feature space that you are in. So without defining a metric space, you cannot really define what is easy, what is hard. Does that make sense? So
yeah, because to add on to Andrea's comment, I think when I saw the example that you showed me in the lecture, it seems like the network focused on those like tiny symbols on the picture rather than looking at the entire picture to reason about this is 2 or 6. So I thought, oh, maybe the network is trying to focus on more the easy part to get the better training examples. I thought maybe that might be one of the hypotheses.
yes, so I think I think there's a lot of recent work also showing that deep networks learn simpler features instead of more complex ones. But the problem is like what is simple and what is complex depends on the feature space that you're working in. And it's very hard to say this is what is simple and this is what is complex. Right? For example, with auto encoders, right? I mean, JPEG compression is one potential representation you can learn, or you can learn the shape and the lighting and so on. So which one of them is more simple, the JPEG compression or segmenting it into an object and light?
In human mind, it might be the light way, but maybe in the machine language, it may prefer JPEG.
So I think that is the trouble, right? So there's a human. So we have a certain notion of what is simple and what is complex, and machines might have a different notion of what is simple and what is complex, right? We are not reasoning in the same space. Right? So I think that is how do we come to a space where both me and like a human and the machine can be in the same feature space and say, well, this is simple, this is complex, right? But that is the problem. We don't have a common communication language in which we can communicate.
Makes sense. Thank you.
So Andrea, I hope some of this is also addressing your questions. If not, feel free to bring it up or, start a discussion. So to put it, more concretely, right? So given a task, suppose I have n features which are there. Maybe hypothesis 1 is about picking up on some set of features, and hypothesis 2 is picking up on some other set of features, right? Now, one thing you can say is, well, DNNs don't find the right solution because they get stuck in a local minimum, right? That is one hypothesis you could have, right? They're not finding what we want them to do because they get stuck in a local minimum. Turns out this is not really true. How do we know this? We know this because what we can conduct an experiment, which was done in this paper 5 years ago, that we can take the data set, for example, ImageNet, and you can shuffle the labels, right? So what random labels means that I take the data set, and to every image, I specify a random label. And what we are measuring is the loss, the training loss to the training steps, right? So what you see is that even if I randomize the data, even if I use random pixels, or if I randomize in any way, I can still get perfect training accuracy or zero training loss, right? Which means is that I'm not getting stuck on any local minimum, right? Deep networks are finding a good solution, but a good solution to the loss function that you're optimizing over. It's just the case that the loss function has many solutions, right? There's some solutions with machines end up finding. There's some solutions which humans end up finding. And given the same data, humans and DNNs can find different solutions. So now to illustrate this, through one more example, from this paper. Now suppose I have this, frog image. When humans look at this image, they would maybe choose, eyes and the color of the frog as a feature to classify it. A neural network might look at some very different features to perform this classification. So we can test, what features are the neural networks using. So for example, I can construct a test set, which is something like this. Now this, humans fail. You would expect them to fail because we can't make sense of this. But networks perform really well because they picked up on some features which are uninterpretable to humans, but help the networks minimize the training loss on the training set itself. Now, if we use this as the test set, maybe both humans and my neural networks work fine because these are natural images. So if the networks worked on all the natural images, then everything would have been fine. But the problem is, I can take a natural image, which say a network predicts with 57% confidence it's a panda. We can add some very small change to this image. So it looks almost the same to a human, right? So I just modified this image slightly. But now the machine ends up thinking of this as gibbon with 99% confidence, right? Now for a human, nothing changed between this image and this image. These are exactly the same for me. But for a network, everything changed, right? Why can this happen? Because networks might pick up on different features to begin with. Therefore, some perturbations, like this perturbation to us, doesn't really change the image, but for a network, it can really change this high frequency features a lot, which can result in a misclassification. For this difference in the features that networks pick up on and humans pick up, not only causes generalization to be bad, but also leads to what is called as poor robustness. Right? That is, if I change the conditions in which my image classifier or my machine learning system needs to work, it is not going to work in an expected way. So robustness and generalization can be thought of as two facets of the same phenomenon. That is, we are not picking up on the right features. And the trouble is, it's not that we cannot come up with a mathematical definition of right. It's just that we don't even know how to define it, because it is human defined, it is subjective. It is not objective. I think that is the struggle which any work or research in generalization has to deal with. And now with that, we'll take 5-minute break. And then when we come back, we are going to look at how do we try to align the solutions between humans and what a network might end up picking up on. So with that, let's take a 5-minute break, and then we'll see each other soon. And in the meantime, if you have any questions or any comments, feel free to put them on the chat, and we can take up for discussion. And we'll meet in 5 minutes. let's start again. Any questions or comments on what we covered until now? No? Okay. So let's see, how we can align human features and, deep learning features. So fundamentally, there are three things, we can look at. One is the data, one is the architecture, third is the optimizer. So first, let's look at data. So let's look at the dominant view, which is there both for generalization and for robustness. Right? The dominant view is that we want to minimize a particular loss function, say L. X is my input, Y is the thing I want to predict, and theta are my parameters. Right? So in order for my system to work on the kinds of images I want it to work, or kind of data I want it to work, what I'm going to do is I'm going to generate different variations of my data. And these variations, let's say xi plus delta xi, where delta x is sampled from some distribution. And what I will assume is that no matter what delta x I choose, my label is going to be the same till the time delta x is sampled from some distribution. Right? And this is what pretty much leads to data augmentation, adversarial robustness, so on and so forth. Right? So these are all different ways of augmenting the data. Right? So what is data augmentation saying? Is saying, well, not only a chair, or not only is this a chair, but all these different ways of modifying the chair are also a chair image. Right? For example, if I was trying to classify a chair versus not a chair. Right? So we are explicitly telling the network what things are the same and what things are not the same. Right? So what we can do is one can go ahead and test, how well do neural networks perform when we train them in some setup, and then we try to evaluate them on some modifications of the image. Right? For example, I'm showing some modifications from the ImageNet C dataset, in which they add these different kinds of modifications like motion blur, zoom blur, so on and so forth. Just putting some noise. So the first thing they look at is how does the performance vary, or how robust are the networks if we go from a shallower AlexNet to more state-of-the-art ResNet. At first, I'm just showing you the error on ImageNet. And as expected, going from AlexNet to ResNet, the error on ImageNet drops. Now we can look at the error on ImageNet C, and we're going to look at the ratio of the errors. So our baseline is going to be AlexNet, and we're going to look at what is the percentage of error do these networks have as compared to AlexNet. So what you might see is over here that, okay, ResNets are getting a lower error on ImageNet C as opposed to AlexNet. So you might think, well, these models are more robust because they're getting a lower error on a perturbed data set. But it should also be noted that they're already doing better on ImageNet itself. Right? So what they also did, this particular paper, they came up with one more metric where they were looking at the gap in how well does the normal model do versus how much does the model do when have images with noise, and compute that difference and compare that with the difference with AlexNet. Why AlexNet? Because AlexNet was one of the first computer vision deep learning model, and all other models have been improvements on that. So if you compute the relative MCE, you find all these numbers are around 100. Right? So although in absolute terms, the performance is improving, the delta between how well these models do on the original image versus perturbed images has not really improved. Right? So deeper networks have lower errors, but depth has not led to more robust models. Right? So that's one concrete takeaway. Now, what has led to at least some robustness has been data augmentation. Now, over here, I'm showing you these different approaches of doing data augmentation, from standard data augmentation to augmix. So augmix is a technique which mixes up many different kinds of augmentations like cropping, rotation, flipping the images, and so on and so forth. Now, if you really want to read about this, read this paper, Augmix, by Dan Hendricks, which came out last year. And so one thing which did work to increase generalization / increase robustness is data augmentation. And this is something we also saw with domain randomization, right? That in order to transfer to a test set, we were doing domain randomization. We also saw it, in context of this pose detection, where to, get good pose detectors for these objects. The way it was randomized is by throwing these objects against random backgrounds, right? So that we can increase the diversity in data. Similarly, we also looked at the example of ProgGen games, where they created these many different variants of the game. And there's a game type, and you're seeing like 9 variants of the game, but in practice, there are thousands and thousands of variants. And if we look at training plot versus test plot for say one of them, with a few levels, which is on the left or on the x-axis, there's a huge gap in training versus test performance. And only as we increase the number of test levels, which is as I'm doing more data augmentation, I'm able to match my training and test accuracies. Right? But one does require around 100,000 levels to close the gap. And not only do you close the generalization gap, but there's another study conducted which looked at how human interpretable are features as we increase the number of levels. And so what they found was, as we're doing more augmentation, as we have more levels, we are also able to get more interpretable features, right? I mean, this is not surprising. Better features are also leading to better generalization. But a caveat with data augmentation is what we saw before, that surely there's no free lunch. That if we augment, then we can generalize to a broader range, but we lose out on peak performance. Right? This is something we saw in the Sim to Real lecture. So overall, if we were to ask the question, what is it in deep learning that we know works for out of distribution generalization? And last year, this paper concluded there's nothing which consistently improves robustness. Right? They tried larger models, they tried attention mechanisms, they tried pre-training on different data sets or diverse data augmentations. The data augmentations by and far seem like a thing which are useful, but again they're not useful everywhere. They're useful in most places, not necessarily everywhere. So in one way, what you can think of how we are building models which are robust or generalized today is almost like finding a needle in the haystack. Now, what do I mean? I know this is how my data looks like, xi, and I come up with all different ways the data could look like, which should have the same label. And we provide this information by specifying data augmentations. Right? If you remember contrastive learning we talked about in the previous lecture, that is one of the best known feature learning method that also critically depends on data augmentations that we choose, right? So they create positive views and negative views. And the way we create positive views is by augmenting the image by either cropping it, flipping it, rotating it, so on and so forth. Right? So we are manually telling the system, this should be same, this should not be same. And what is and good open research areas really understand, why is it that deep networks find some solutions and not other ones? What are the properties of those solutions? So that we can fundamentally maybe change deep networks, one day to make them learn features which are more human aligned. So, that's what I'm going to say about the data. That, what we know with the data is to collect unbiased data as much as possible. But even if we have unbiased data, you can still learn spurious features. And the way that we know in deep learning to get around it is by augmentation. And that's all we know as far as data is concerned. The second is optimizer. So this is an active area of research. How does the optimizer affect what features one learns? I'm going to just present a result from one of the papers so that you know about this research area and you can look up if you want to look up on your own. For example, this paper suggested that if one uses small learning rates, then networks can find easy to generalize but hard to fit patterns, versus if you use large learning rates, you can fit much more easily. That is, your training loss is going to go down much more easily, but it's going to be harder to generalize. Right? The point being that these small things that you may not think affect your features actually do affect the features. Right? So this is an active area of research on optimizers. If you want one paper that you can seed your search from, look at this paper. The third thing is about the architecture. Right? So one thing you can say is, well, instead of having these deep networks which process the image and then they directly try to do these control tasks, we know something more about the world. We have some priors. We know that world has objects, the world is 3D, and so on and so forth. So why don't we leverage that information? Maybe if we leverage that information, we put in these priors, these deep learners are going to learn more human-like features and therefore generalize better. This sounds very reasonable. So let's consider, for example, objects, right? So over here I have a game, I have this sprite, I have to go to this door, and I have to avoid, these enemies like the pink sprite and the spikes. And to get to the door, I need to get the key. Right? So maybe what I should do is I should first segment this out. So I have a segmentation mask. I know these are my ladders, these are my platforms, this is my agent, and so on. So now we have two games, game A and game B. And the question I have is game A easier than game B for an RL agent? Or is it equally hard, or is game B harder? Unfortunately, I didn't make a poll for this particular question. Otherwise, I would have done a poll. But if people want to post on the chat. Yeah, so the question is A harder than B? You can just answer yes if you think, sorry, the question I have is game A easier than B? So if you think game A is easier for an RL agent, you should say yes. If you think no, then you should say no. So Andrea, you said depends on the model. Do you want to maybe elaborate a bit more what you mean by depends on the model? No. So seems like hard to parse floats separately from other blocks. So the CNN is pre-trained. So let's assume right now, we are training from scratch. And we have these games A and B, we are training from scratch. And we would like to know what happens between game A versus game B. So, give it some thought. But turns out I'm going to skip to the answer for now. You can conduct an experiment where you have RL agents play the version A or the version B, and you can measure how much time they take, right? Turns out that, that for an RL agent starting from scratch, both of these game versions are equally hard, right? The agent does not, even though you give it these objects, the agent still needs to learn how to make use of these objects, right? So just having objects by itself is not sufficient, right? It's like saying I am giving the network some information, which is these are the objects, but the network also needs to learn how to use that information, and that takes learning to happen, right? So that's why if you just compare the performance on these games from scratch, you don't end up getting any difference in performance, right? So only if you were to pre-train and then go to new games, you might see that transferring on games which look like game B might be easier than transferring on games which look like game A. Right? Once a network has learned how to use the information about what is an object, it can transfer. But to learn what is an object, even though you give it as an explicit channel or as a separate entity, requires effort. Then a more, philosophical or a high level, question which comes up is, what exactly is an object? Right? I mean, for example, if I consider, this game, many of us will agree that this is an object, right? What about this? I mean, okay, this is a bullet, should be an object. Is this an object also? I mean, it looks like a blob, which is, coherent. Or what about this? Is this an object? Or what about this? Or for matter this, right? Are all of these objects, or are only these things, the bullets and the enemy, the objects, right? Or, if I show you, an image of a tree, or if you're driving down a road, then the whole tree for you is an object because you want to avoid it, right? But if you were to pluck fruits, then suddenly each branch becomes an object, right? But if you were to draw, then not just the branch, but each leaf becomes a separate object. What is the point I'm trying to make? The point I'm trying to make is the definition of an object really depends on the task that you're doing. Right? To give one more example, suppose if I ask you to move the candies, right? Then the whole object, right? This whole bowl with all the candies is one object. If I say, give me a candy, then each of these individual things is a separate object. Versus if I say, let me eat the candy, then suddenly this one object becomes two, the wrapper and the object, right? So, talking about what an object is without defining a task is extremely hard, right? So in some ways, we have this prior information that we think should be useful, that there is an object. But turns out this object is a very abstract notion. And to make it concrete, you really need to know what the task is. Right? And that is what poses a fundamental difficulty on using, say, objects as a prior. In some scenarios, what an object is very, very clear. In those scenarios, yes, you can use or define or identify what the object is and use it. In many scenarios, like even in these games that we were seeing, right? If I just use a state of the art or off the shelf OLE detector, it's going to detect all of these things as objects. Now, if I get so many objects, then the whole point of objects being some few parts of the image which is important will no longer hold true. Like a lot of spurious things will also be detected as an object. But this is something which is not just limited to some things like an object, right? I mean, if you consider another information that you believe could be useful, for example, the fact that world is 3D, you can ask the question, what is 3D? For example, if I have a self-driving car going on the road, then by 3D, I mean how far away something is, which is depth, to avoid collisions. If I'm trying to do rendering, then a mesh is a very good representation of 3D. Versus when I'm trying to grasp an object, what I care about are surface normals, so I can decide where to go and put my fingers so I can grasp the object. So again, depending on the task, the exact definition of 3D changes, right? So, which has an implication that if, as an AI designer, I want to implement 3D, can I actually implement things like what is an object, what is 3D without a task? And one suggestion over here is that you cannot, because these representations are actually task specific. Right? And this is the challenge when you try to reason about AI systems in terms of representations. And if you really want this viewpoint, you should read this paper, which is an excellent paper from Rodney Brooks around 20 years ago, written Intelligence Without Representations. Right? It tries to provide a plan or an overview of how or why thinking about representations is very hard, and why we may not think in terms of representations, but in terms of behaviors. The reason being, it's very hard to specify, representations without specifying a task. And then we all know that specifying a task is also very hard in the first place, right? So it's a chicken and the egg problem in some ways, right? A similar flavor we saw in the last lecture, because we were talking about what is a model, right? We said that if you're navigating, the model might be the occupancy map of where an obstacle is, where is free space. If I'm pushing objects, then Newton's laws are the right model. When we are playing a game, then the rules of the game are the right models, right? Again, depending on the task, what a model is different. It's not always given an image XT, action 80, let me predict the next observation. Those are not always the best models that one could be constructing. So, that is the fundamental challenge in, trying to incorporate some architectural priors that we know from humans are good into deep networks. Right? I mean, there's some architectural priors which have worked out fine, which are like convolutions, right, or pooling, and so on. Right? Or, for example, architectural priors like self-attention, and so on. But these architectural priors are not in terms of representations. Right? I think the hard part happens when you try to impose that your network should learn a particular kind of representation, because defining that representation itself is non-trivial. So any questions or comments on this part? No? Everyone agrees? No one is, no one wants to be controversial over here and say, no, I can define objects, or I can define 3D, or I can define models. Everyone is in agreement? Come on. Okay, well, maybe everyone needs an afternoon coffee. So, okay, well, let me wrap this up with, so, then what do we do, right? I mean, okay, there's some things we can do with the data. There's some things we could do with the architecture, but typically putting the kind of constraints which might make features more human-like is hard to do. We saw something about the optimizer. The other thing, we can also look at is the objective function. Maybe, maybe we can define objectives and find a good objective function which will lead to emergence of human-like features or human-like representations. Right? And this has what has inspired some works to try to recreate evolution, or in some ways emerge intelligence or intelligent behaviors by making agents compete with each other. Right. So some examples of these works are, for example, getting this ant and the spider to fight against each other, and because they are fighting, in the process of fighting they end up learning some skills of trying to throw each other out or trying to defend themselves and so on and so forth. Another example of trying to use competition as a way to get behaviors to emerge is this work from OpenAI, where there's this blue team and there's the pink team. Right? So the pink team is trying to kill the blue team. And so initially what happens is, this blue team, puts this, these boxes so that the pink team cannot enter and cannot kill. Right? Then, the pink team realizes this. Then what the pink team does is, the orange team or pink team, it climbs up, it uses a ramp, it climbs up, then it comes and kills the blue guys. Right? The blue guys realize, because of this competitive nature, that okay, this ramp is what is allowing the orange team to come in. So what then they do is they bring this, then they kind of bring this ramp in so that the orange team cannot come and kill them. Right? So what this line of work or these kind of works are showing is how, or they are investigating that by trying to make the environment complex and just by having agents compete with each other, maybe we can evolve some intelligent behavior, which kind of circumvents two issues. One is I'm not explicitly defining a task. My task is very simple. It is just survival. And it is the complexity in the environment and the competition which is leading to these behaviors. And second thing is I don't even have to specify what the representation is. The representation is something which is emergent. Now, what's the downside? The downside is that these works require massive amount of compute, right? And then you need to really engineer the environment for this complexity to emerge. For example, if I did not have the ramp, then you wouldn't really discover this hide and seek kind of behavior to the same complex level as you're seeing in this game. Right? So there's a lot still unknown about what kind of environment designs will lead to generalizable or intelligent behavior. Right? So this again is an interesting research area of what are the properties of the environment that will force generalizable behaviors to emerge. So people have been looking at this. Like for example, a practical setup where this could be useful is, suppose I want to design a quadruped robot which can walk on a bunch of terrains. So now instead of trying to just optimize the robot, we can optimize both the terrain and the robot simultaneously. Right? So as this agent becomes more complex, these terrains will also start becoming more and more complex. Right? So that, tries to again circumvent, that I don't have to define, a task which is, like cross the gaps or cross this kind of a terrain. I let the terrain also be a variable in my environment. And obviously an open research question is, can we scale them beyond these toy environments? And this is where I'm going to stop today. And it's also, I think we are right on time. I see there's some questions on the chat. So now I'll take those questions. And it is also office hours.